All right, so let's talk a little bit about notation. Each term in a sequence can be labeled as A1, A2, A3, A4, and so on, right? Or it may start at A0 such that it's, A0, A1, A2, A3. So if you go up here to this sequence here, like 1, 3, 5, 7, 9, I could call this A1, A2, A3, A4. So I know this is term number 4 and so on. Or, I could call them I could label them starting at 0. So this could be A0, A1, A2, right? So it'll be like 1 off almost if you start at 0. A generic term is called AN, A sub n, okay? So if I'm going to talk about like a random person, right? Like it's like Jane Doe. If I'm going to talk about a random term in a sequence, it's A sub n, okay? That's the Jane Doe of terms, Okay, now, suppose I have a sequence here, right? Let's write down a sequence. 1, 3, 5, 7, 9, 11, 13, and so on. All right? And now, suppose this is A sub 1, 2, 3, 4, 5. Okay, so this is A sub 5. Okay? If that's A sub 5, what would be the name of the seventh? Of the number 7, A sub what? A sub 4. How did you know to do that? Right, but if, like, the 5, right? A sub 5, the one that comes right before it has one number lower, right? So what's the name of the 11? A sub what? 6. A sub 6. So how did we do that? For the 4, we took the 5 and we did minus 1. Here, we took the 5 and we did plus 1. Okay? Now, let's change things up a little bit. Suppose this was not A sub 5. Suppose that was A sub n. Okay? What would 11 be called? Yeah. A sub n plus 1. And what would 7 be called? A sub n minus 1, right? So that's what I'm talking about here. Terms that come before or after A sub n are called A sub n minus 1 or n plus 1, respectively. Okay? So look at this sequence here. This is A sub n, right? Right in the middle of it is A sub n. The one that comes right before it is A sub n minus 1. And then n minus 2, and then the ones that come right after it is A sub n plus 1, n plus 2, and so on. Okay? So that's how I label terms. So for example, this is A sub n. What would like 5 numbers down be called? A sub n plus 5, right? I know I'm sort of insulting your intelligence here, but it's just to prepare us for what's coming in section 4. I really want you guys to be comfortable with that notation, okay? All right. Okay, so let's talk about how we generate some terms. A sequence can be represented as a function, right? And here, an will be the nth term, as we've talked about. Okay, there are several different types of formulas. An explicit formula gives you the nth term as a function. So an explicit formula is something where, let's say I wanted the 52nd term. I have the formula, I put some numbers in there, and I can find the 52nd term. All right? Take a look at this one. This is an explicit formula. It says A sub n is that. And now we want to find A sub 4, okay? So we want the 4th term in the sequence. So A sub 4, right? Take a look at this. N is 4 right now. So every time I see an N, I'm going to plug in a 4. So A sub 4 is equal to 13 over 2. Okay, let's talk about what we've done. Hey there. Okay, let's talk about what we've done. This is a sequence, right? This is the first term, second, third, fourth. I don't know what any of the three numbers are, but I know that the fourth term is 13 over 2. Okay? That's what I just found.
Is that how we, one more answer the problem, where would you want it to be left in? Where would you want to be left in the A, and A sub 4 over 14 halves?
Yeah.
Or would it be like 13 or 15 half over A sub 4?
No, so that's not really over. It's like that space is a space holder. So you could just say A sub 4 is equal to 13 over 2. Okay, this is how we would place it. Here, it says to find the next 4 terms in the following sequences. So you're given, this is a different example now. In example 1, we didn't know anything. All we had was an explicit formula in order to find like specific numbers. Okay, lean forward. In this one, we're given a couple of them, and we have to, based on what we're given, we have to recognize a pattern and figure out some of the other ones that follow. Okay? In fact, it wants the next 4 terms in the following sequences. Okay, now, there is no cookie cutter way to do this. Is there one way to figure this out? Yes. I have had students who look at something like this and they're like, oh yeah, I know what the pattern is, blah, 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 blah. I have some students, and you know, me included as a student, I would really have to like stop and think and try some things out. Okay? Either way, it doesn't matter how you get to it, we just get to it. So let's see some things. What you want to do is this. Okay, I have a 3 here. What do I do to the 3 to get -1? What's one thing I can do? Subtract 4. Okay, so now see if that holds for every single one that comes after that. If I subtract 4, do I get -5? Yep. If I subtract 4, do I get -9? Okay, so that's the pattern, is subtract 4. Okay, so the next 4 are going to be -13, -17, -21, -25. Okay, all right, what about the next one, B? How do you get from 2 to 5? What do you do? Add 3, and then what do you do? Add 5, and then what do you do? Add 7. So what's the pattern? Okay. So we're adding what? Consecutive what numbers? Odd numbers, right? We're adding consecutive odd numbers. Consecutive odd numbers. That's a good phrase to know, consecutive odd numbers, for section 4. Okay? So what would be the next ones then? Uh-huh. Uh-huh. 65. Okay? Good. All right. Here, it says to find the next 4, right? And all we're given is an explicit formula. So to find the next 4, we're not really given anything, so we're going to find the first term, then the second, then the third, then the fourth. So A sub 1, here n is 1, so I plug 1 in for n, and I get 2. A sub 2, now n is 2, I plug 2 in, and I get 9. A sub 3, now n is 3, so 3 cubed plus 1. And then 4 cubed plus 1 is 65. All right? So the next 4 terms are 2, 9, 28, 65. For these, you want to list like a sequence. So one thing I failed to mention is in a sequence, the terms are separated by commas. Let's put that here. Okay, so terms in a sequence are separated by commas. All right? Yes. We normally start with 1. Just specify. If it's not specified, start with 1. Okay. You'll find that most of the time it won't really be an issue. Okay. So these were explicitly defined functions where, okay, if I want like the 4th term, I could go directly to the 4th term. I don't need to know what comes before. I don't need to know what comes after. Like, right? Like you see in example number 1, we needed the 4th term and we went straight to it. I really didn't care about the 3rd or the 5th term or any other term for that matter. Okay? That's an explicitly defined function, sequence. Now, a recursively defined sequence is a little different. What's the term recursive? What does that word mean, recursive? Like just in plain English, yeah. Repeating, right? And repeating backwards and recurring, like, so basically, if something goes backwards or if something recurs, it has to do with what happened before, right? That's what recursive functions are. Each term depends on what happened before it. Okay? So, not really. Not really, because, no, not really, because if I just wanted to find a sub 3, I didn't have to find any of the other ones. Yeah, there we were just looking for a pattern. Yeah, there we were just looking for a pattern. Here, so recursive sequences, so terms depend on those that came before. So, to find a recursive function, we're going to have a few initial values, after which each term is defined using the first couple. So, look at an example of a recursive formula. It's a little bit more intricate, right? Look at what it gives you. It gives you the first term, a1 equals 1, okay? And then look at how the next term is defined. A sub n is equal to a sub n minus 1 plus 2. What does a sub n minus 1 mean? It's the number before. The number immediately before. So to find a term, you have to go to the one immediately before it and add 2. Okay? All right, so take a look at this one for a minute. Look at example 3. It says find the 4th term of the recursively defined sequence this. Okay, a1 is equal to 3. All right, so this is what you're given. a1 is equal to 3. And then each term after that, all right, is 3 times the term that came right before it minus n plus 2. All right, so let's do one here. I want to find a sub 2. Okay, what's n here? 2. All right, so here's what I'm going to do. 3 times a sub n minus 1, the term that came right before it, so 3. Okay? Minus n we said was 2 plus 2. So that's 9. Okay? No. Because it's n plus 2 and n is going to change. But 2 is not. Yes?
Would A always be 3?
No, because now it's going to change. So look, now it's going to change. Now here, n is equal to 3. So the formula says 3 times a sub n minus 1, the term that came right before. What's the term that comes right before? Huh? 9. Right? And then minus 2 plus 2. Sorry, yes, minus n, which is 3 plus 2. Right? So how much is that? 26. So do you see the recursiveness of it? Each term, in order to generate each term, you have to go and look at the term right before it. You can't just jump to term number 51. All right, so let's do another one. A sub 4, what's n now? What's n? N is 4, so it's going to be 3 times how much? 26, right? The term that came right before, minus what? Minus 4 plus 2. And that'll make it 76. All right, and that's what we need. We wanted the fourth term, so a sub 4 is 76. All right, so again, let's appreciate the difference here between example 1, where I wanted a sub 4, I jumped right to it. And then this one where I want a sub 4, no, I needed at least the term right before it, okay, in order to generate it, okay? Well, it can be. It just depends on how the recursive function is defined. So in this case, it's a sub n minus 1 plus 2. It could have been a sub n minus 2 plus 2, right? It could have been like the 2 terms before plus 2, okay? It depends on how the sequence is defined. Okay, one of the most famous recursive functions is the Fibonacci sequence. Anybody know? Anybody heard of the Fibonacci sequence? Uh-huh. Yeah. That really weird infinite thing. Okay? The spiral. So for example, the Fibonacci, yes, good. You say it louder, very loud. Yes. So each term is the sum of the 2 that come before. Okay? 2, 5, 3, etc. So lots of applications of it. Let's do this, and then we'll talk about some applications or some places in nature where we see it. Okay. So look at this one. The Fibonacci sequence is this. A1 is 0. A2 is 1. Those are the 2 given. And then every other one, A sub n, is A sub n minus 1 plus n sub n minus 2. So if I have A sub n in relation to A sub n, which one is an minus 1? The one before. Which one is A sub n plus 2? Right, 2 before. Okay? So look at how it works. Okay, so A1 is 0. A2 is 1. A3, we have to add the 2 that came before it. 0 plus 1, 1. A4, the 2 before it. 1 plus 1, 2. Right? So what's A5? Let's just continue. What's A5? 3. What's A6? 5. Right? Here we wanted A4, but, we went a little bit before. We went a little bit more. Okay, so when you plant a brand new tree, right? First it's got like 1 stem, and then you have, at the first level, you have 2 branches. Look, when you plant a new tree, right? You've got 1 branch. Then at the end of then you've got still the 1 branch. Then you've got another branch grows, so now you've got 2. Then another one grows, so now you've got 3. Then, each one sprouts a little bit more, so you've got 5. And then each branch sprouts another one, so you've got 8. And then if it continues like this, it'll be the Fibonacci sequence. Isn't that cool? Come on, that's so cool, right? And then same with the spirals here. Same with like petals on a flower. I mean, it's everywhere in nature. Well, I'll try to do a little bit more later. It could be, yeah. It's a very sad thing that we don't have enough time. Okay, so similar to functions, the terms in a sequence might eventually approach a specific value. We call that a limit, okay? If the terms in a sequence, if the terms of a sequence approach a unique number, then we say it has a limit and we say it converges. All right? Take a look at this one. Take a look at this first block here on the right. On the left. The first term of this sequence is 1. That's a sub 1. The second term is 0.4-ish. The third term is 0.2, a sub 3. Then you have a sub 4, a sub 5, right? This is a sub 5. This is a sub 10. This is a sub 25. What is the value of a sub 25? How much is it? Estimate. 0 point something something. So as I'm generating more and more numbers, what is their value getting closer and closer to 0? It looks like it's going further and further and further down to 0. This is a sequence whose terms converge. Okay, so this sequence we say converges. Okay? You're going to get back to this when you take Calc 2 or Calc BC. Okay? Convergent and divergent series and sequences. So this we say converges. All it means is the values of the terms are getting closer and closer to some other number. If it's not approaching a specific number, we say the sequence diverges. Look at this one. Here's a sub 1 and then a sub 2 and a sub 3 and a sub 4, and then it goes 5 and 6. And look at this one. Does it seem like, there is a pattern where they're approaching the same number, like a specific number? No. So this is one where it's divergent. All right? So we're going to do a couple of examples, and we're just going to test and see whether something is convergent or divergent. So what I want us to do is I just want us to generate numbers and see, where everything is going to end up. Okay, so this is the explosive formula for a sub n. Let's find some numbers here. A sub 1, right, how do we find it? Is negative 4,000, negative 1 over 4 to the power of 1. And that value is positive 1,000, right? Because it's negative 4,000 divided by negative 4. Okay. A sub 2 is negative 4,000 times negative 1 over 4 squared. What's negative 1 over 4 squared? Positive 1/16. So it's going to be negative 4,000 divided by 16. Is that going to be a positive or negative value? Negative 250. Okay? A sub 3 is negative 4,000 times negative 1 over 4 cubed. Now you tell me, is a sub 3 positive or negative in sign? Positive 62.5, in fact. A sub 4 is negative 15. A sub 5 is 3.9. A sub 6 is negative 0.97. Okay, let's just stop there. Let's plot these. So first, a sub 1 is 1,000. Then negative 250. Huh? Negative 250 is further down. A sub 5 is 3.9. A sub 3 is how much? 62.5. A sub 4 is negative 15. 3.9. negative 0.97. Okay, so does it look like eventually it's going to converge to a specific value, or does it look like it's going further and further away in random directions? It's going to converge to what, do you think? 0. Because look at what's happening. We started very high up, okay, away from 0. Then it was close. Yes, it's oscillating in sign, right? Then it goes closer to 0 and closer to 0, closer to 0, closer to 0. So from either side, it's approaching 0 eventually. So eventually, it's going to get closer and closer and closer and closer to 0. So this is one that is convergent. Okay, so this one converges. Now, notice the alternating sign, right? How do you know if, so look at this one. This is negative, negative, positive, negative. So we have positive, negative, positive, negative, positive, negative. Could we have known that this was going to alternate in sign from the formula? How? What would be a giveaway? Yes. Exactly. That's it right there. Here we have some negative term raised to an exponent. Okay? Negative term raised to an exponent will alternate sign. Right? Because if you have negative to the power of 1, it's negative. Negative to the power of 2, it's positive. 3, it's negative. 4, it's positive. Okay? All right. Take a... Yeah.
Would a problem like that be on a calculator to make up
okay, so this specific one would be calculator. But I could have something similar where you don't get, you know, those little itty bitty decimals where that could be non-calculator. There are no tissues, but there are some not used, unused napkins. There are no tissues there. Okay. Take a look at B. Is this going to be one where the sign alternates or no?
Yes.
Yes. Okay. So, yeah.
Does it always have to approach like converge at 0?
No. Good question. Very good question. No, it doesn't always have to converge to 0. It could converge at like 3. Yeah.
If it alternates signs, is it always convergent?
No. Okay. Negative 2 to the power of 1. So this one here, for example, this you could do without a calculator, right? Because this one is negative 2 over 2, negative 1. A sub 2 is negative 2 squared over 2, 4. A sub 3 is negative 4. I'm going to give you the terms here. I'm sorry. A sub 2 is 2. And then A sub 4, 8. Fifth term, negative 16. Sixth is 32. Negative 64. And I have 8 terms here, 128. Right? So these are powers of 2 divided by 2, easily done by hand. Okay, so here's what we have. I have negative 1, which is like way there, okay? And then I have 2. And then I have negative 4. And then I have 8. And then negative 16. And then 32. 10, 20, 32. And then I have negative 64. And then I have 128. So what do you guys think here? Convergent, divergent? Is it approaching a specific value?
Well, it is that way.
Huh?
If you're going from right to left.
Uh-huh. Well, we always read functions left to right. Right? Yeah. So it's divergent because we don't know, like it's oscillating, and then eventually it's going to be a much lower negative and then a much higher positive and then a much, so it's going to oscillate. So this is one that's divergent.
We can see that it's going to be divergent after the
3 or 4 is a good number to do because, okay, 3 or 4 is a good number. Okay, so this one, A sub 1 is 0.1. And then it's 0.00067, 0.00006, And then here we have point, 4 zeros, and a 57. Okay, and look at how I've calibrated this. It starts with 0.1, and then it goes to like 0.067, which is here, and then eventually it's going down. So what do you think? As n is increasing, what's happening here? It looks like it's getting closer to what? 0. So this is one that's going to converge. Okay? So your homework for tomorrow, yes, your homework for tomorrow will be the first part of this until number 19. So 1, 2, 3, 4, 5 of them. Okay? And then you will have the rest due the following day. Okay, so I will take 2 days for this, but then 1 day for each of the rest of the sections. Okay? All right.